Hi everyone, how are you today? Let's learn cognitive psychology with me. Today, we will learn about recognizing objects. Let's get started. There are some disorders due to brain damage. For example, apperceptive agnosia, associative agnosia, and integrative agnosia. Apperceptive agnosia. People seem to be able to see an object's shape, color, and position, but they cannot put these elements together to perceive the entire object. Associative agnosia. People can see, but they can't link what they see to their basic visual knowledge. Integrative agnosia derives from damage to the parietal lobe. People appear to be normal in tasks to detect features in display, but they are impaired in tasks to judge how the features are bound together to form complex objects. On the right-hand side, you can see the picture of brain. There are some parts here, for example, frontal lobe on the left-hand side, and then you can see parietal lobe, occipital lobe, temporal lobe, spinal cord, and cerebellum. Integrative agnosia derives from damage to the parietal lobe. You can see that parietal lobe here is on the right-hand side. Recognition. The variations in the stimulus input give our first indication that object recognition involves some complexity. Object recognition is influenced by the stimulus itself, the features that are in view. Processes shaped by the stimulus are data-driven and involve bottom-up processing. On the other hand, top-down processing is concept-driven. Top-down processing is concept-driven. It is influenced by our knowledge and expectation. That means in top-down processing, we see things based on our own knowledge and thoughts or experience. The importance of features. Recognition starts with the identification of visual feature in the input pattern. For example, vertical lines, curves, diagonal. Then you can start assembling larger units. For example, if you detect 4 right angles, then you know it's a square. Concentrate on elements shared by various features. For example, various A's to enable us to recognize A's despite their apparent diversity. The importance of features. Features are important in data from visual search tasks in which participants are asked to examine a display and judge whether a particular target is present in the display or not. Word recognition. Object recognition starts with the detection of simple features. Factors influencing word recognition: familiarity and recency of view. Familiarity means how familiar a stimulus is to you. An older research used tachistoscope, a device to present a stimuli for a precisely controlled time. More modern research uses computers, but the displays are still called tachistoscopic presentations. Recency of view. If the participants view a word, then view it again later on, they will recognize the word readily the second time around. The first exposure primes participants for the second exposure. This is called repetition priming. The word superiority effect. The advantage of perceiving letters in context, the word superiority effect, or WSE, word superiority effect. Recognizing an entire word is easier than recognizing isolated letters. Well-formedness. Well-formedness. Well-formedness is a good predictor of word recognition. The more English-like string is, the easier it will be to recognize the string, and the greater the context benefit the string will produce. Misspelled words are often read in a way that bring them into line with normal spelling. For example, when you see this word on the box here, CQRN, how do you read it? CQRN is read as corn, even though it's actually Q, not O. Future nets. What are future nets? It's a network of detectors organized in layers. At any point in time, each detector in the network has a particular activation level, which reflects the detector status at that moment. Let's look at this diagram. You can see how it works here. A detector receives an input, then its activation level increases. This activation level will reach the detector's response threshold. Its activation level increases. At that point, the detector will fire, send a signal to the other detectors to which it's connected. On the left-hand side, you can see a picture of a simple future net, for example, clock. You see on the bottom, the future detectors, you can see some symbols like curve, their shapes, curve shapes. And then above those curves, you see CLOCK. They are letter detectors. And then you see the word clock, the word detector. Here is an example of a future net. Here, the future detectors respond to simple elements in the visual input. When the appropriate feature detectors are activated, they trigger a response in the letter detectors. When these are activated, in turn, they can trigger a response in a higher level detector, such as a detector for an entire word. Future nets. Some detectors will be easier to activate than others. Some will require a strong input to make them fire, while others will fire even with a weak input. It all depends on how activated each detector is. Activation level depends on the principles of recency and frequency. For frequent words that you often see, the detectors needed for recognizing these words have been frequently used, so they have high levels of activation. Repetition priming also works that way. Presenting a word once causes the relevant detectors to fire. Once they have fired, activation level will be temporarily lifted because of the recency of use. Therefore, only a weak signal is needed to make the detectors fire again. Thus, the word will be more easily recognized the second time around. That's repetition priming. Future nets. Bigram detectors. Bigram detectors are detectors of letter pairs. The detectors are triggered by lower level detectors and send their output to higher level detectors. These detectors will fire with only weak input if you already have high activation level at the start. For example, although you have never seen the sequence of highs before, you have seen the letter pair high in hit, so the detectors need no much additional input to reach their threshold. On the right-hand side, you can see an example of bigram detectors, clock. Let's see from the bottom part. It seems plausible that the network includes a layer of bigram detectors between the letter detectors and word detectors. On just the bottom part, you can see feature detectors. Here you see the features of the curve shapes. Above them, you can see CLOCK, the letter detectors. Above the letter detectors, you can see CL, LO, and CK, which are the bigram detectors. Then above the bigram detectors, you see the word detector clock. Distributed knowledge. The knowledge about bigram frequencies is contained within the network via a distributed representation. It's knowledge that's represented by a pattern of activations distributed across the network and detectable only if we consider how the entire network functions. The McClellan and Ramerhart model. This network can identify well-formed strings than irregular strings. They are characters in context as opposed to characters in isolation. Excitatory connections in red arrows are the connections that allow one detector to activate its neighbors. For example, detection of T excites the trip detector. Inhibitory connections are connections that inhibit a detector. For example, detection of G deactivates or inhibits the trip detector. On the right-hand side here, you can see the picture of an alternative conception of the future network. Recognition by components or RBC model. This model includes some innovations, including the inclusion of an intermediate level of detectors sensitive to geometric ions. Geons are simple shapes, like cylinders, cones, and blocks, that can be combined in various ways to create all the objects that we see. You can see on the right-hand side, there are some pictures actually of geons and objects. The shapes in geons here are cones and blocks. Then on the right-hand side, you can see some examples of what the objects can be made of from geons. Panel A shows 5 different geons. Panel B shows how these geons can be assembled into objects. The numbers in panel B identify the specific geons. For example, a bucket, number 5, contains geon 5, top connected to geon 3. Recognition based on geons is viewpoint independent. This means that no matter what your position is relative to a dog, you can identify its geons to identify the dog. Recognition via multiple views. Recognition sometimes requires mental rotation. Thus, it will be slower from some viewpoints than from others. Therefore, the speed of recognition will be viewpoint dependent. You can recognize an object from many different angles, and your recognition is fast. However, data indicate that recognition is faster from some angles than others. This is consistent with this multiple views proposal. Still on the recognition via multiple views, there is a hierarchy of detectors, with each successive layer within the network concerned with more complex aspects of the whole. Thus, lower-level detectors respond to lines at certain orientations. Higher-level detectors respond to corners and notches. At the top of the hierarchy, there are detectors responding to the sides of the whole object. These detectors each represent what the object looks like from a particular vantage point. The detectors fire when there is a match to one of these view-tuned representations. Debates between RBC approach versus multiple view approach. RBC approach, or recognition is viewpoint independent, versus multiple approach, which means they believe that recognition is viewpoint independent. Viewpoint dependent. RBC approach, recognition is viewpoint independent because you can see an object still same regardless where you are, versus multiple approach. I make a typo here, sorry. Recognition is viewpoint dependent because it depends on how you see it, from which point of view. It can be faster or slower to view an object, which means recognition is viewpoint dependent. According to multiple approach, both sides are correct. Some brain tissues are sensitive to viewpoint, some brain tissues are not sensitive. Face recognition. Prosopagnosia. Have normal vision, but can't recognize individual faces, including their own family and themselves. It's the result from brain damage. But in some people, it appears to be present from birth without any detectable brain damage. Super recognizers. They are accurate in face recognition, although they have no special advantage in other perceptual memory or task. Face recognition is dependent on orientation. It shows a powerful inversion effect. The fusiform face area, or FFA, is responsive to faces. Humans have a specialized recognition system crucial for face recognition. This system involves the FFA in the brain. Damage to this can cause prosopagnosia. Holistic recognition. Face recognition depends on the holistic perception of the face. It depends on the face's overall configuration, the spacing of the eyes to the nose, etc. Several brain sites important for face recognition are the fusiform face area, or FAA, the occipital face area, or OFA, and the superior temporal sulcus, or FSTS. Several brain sites important for face recognition are FAA, OFA, and FSTS. That's a repetition. Top-down influence on object recognition. Top-down effects. Effects driven by your knowledge and expectation. Priming from recency and frequency of use ensures that detectors that have often been used in the past will be easier to activate in future. This way, the network learns which patterns are common and which are not. The network is more receptive to inputs that follow the usual patterns. What about priming? What priming involves? The person needs to understand each word in the instruction, otherwise it won't work. For example, if you do an experiment in, let's say in Swedish, but the participant doesn't understand Swedish, then it won't work. The person needs to understand the relations among the words in the instruction. Summary. Object recognition is not an isolated process. The knowledge external to object recognition, for example, knowledge about what's edible, etc., is imported into and influences the process. Top-down priming draws on knowledge from outside of object recognition itself. Your knowledge, memory, and thoughts from your life experience are important for this sort of priming. That's the end of the lesson today. Thank you so much for learning psychology with me. See you next time.